Have you ever wondered if an AI can actually tell when it's right versus when it's just, well, making stuff up? Today, we're going to dig into a breakthrough method that doesn't just ask that question, it uses the answer to make these powerful AI models way more efficient and a whole lot more reliable. Okay, let's dive right in.
So this right here is the fundamental question, isn't it? It's not just about an AI spitting out the right answer. It's about it knowing how certain it should be. And honestly, this has been a massive hurdle in AI. Because an AI that's wrong but sounds totally confident, that can be way more dangerous than one that just says, hey, I don't know.
And this slide just illustrates the problem perfectly. Take a look at this super simple math question. On the left, you've got a correct logical line of reasoning. But on the right, you see a complete misunderstanding of what half even means in this context. And the scary part? The AI doesn't hesitate. It gives that completely wrong answer with the exact same apparent confidence as the right one. This is the core problem researchers are trying to fix. How do you get the AI on the left every single time without ever getting the AI on the right?
So, the first big idea to fix this? Well, it was basically a brute force approach. The thinking was pretty simple. If you just ask an AI the same question enough times, the correct answer should bubble up to the top eventually.
And this method has a name: self-consistency. It's pretty straightforward, really, just a three-step process. First, you get the AI to generate a whole bunch of different ways to answer the same question. Then, you just tally up all the final answers it came up with. And finally, you pick the answer that shows up the most. It's basically democracy for AI, majority rules. And you know what? It works, but, and this is a big but, it comes at a huge price.
To make this real for you, the researchers shared this hypothetical. For a model that's only right about 60% of the time on its own, you would need to generate 40, that's 40, different answers just to get to 90% accuracy using this majority rules method. I mean, think about that, 40 samples for one question. That is a staggering amount of computation, making it incredibly expensive and really, really slow. Okay, so the brute force method works, but it's just way too expensive. And that got researchers thinking, what if there's a smarter way? What if, instead of treating every single answer the same, the AI could actually tell us how confident it is in each one? And that is the heart of this new method, called Confidence-Informed Self-Consistency, or CISC for short. Instead of a simple majority vote where every answer gets one vote, CISC does a weighted majority vote. So answers that the AI itself thinks are high confidence get more weight. They get more say in the final result.
Now, I love this analogy on the slide because it just makes it so clear. Self-consistency is like a pure democracy. One response, one vote, doesn't matter how good it is. CISC, on the other hand, is a meritocracy. A well-reasoned, high-confidence answer gets more votes. It's an intuitive upgrade that should make the whole thing smarter and way more efficient. It should have been a slam dunk, but it led to a very surprising twist.
So when the researchers started testing out different ways for the AI to express its confidence, they ran headfirst into a paradox, a result that just seemed to defy all logic. Okay, let's break this table down, because this is where things get really interesting. On the left, you've got two different ways the AI can tell us how confident it is. Verbal confidence is basically just asking the AI to say, I am 95% confident. P-true is a more internal, complex probability score. Now, that middle column, calibration, measures how honest the AI is. A lower score is better. It means the AI's stated confidence actually matches its real-world accuracy. And look, verbal confidence is almost perfectly calibrated. But then you look to the right, it barely improved things. Only a 10% cost reduction. Meanwhile, the less calibrated, less honest P-true method, it delivered a massive 46% cost reduction. This makes absolutely no sense, right?
This is the mystery at the heart of it all. Why would the most honest, the best calibrated confidence method be the least useful? It's a total paradox. The method that looked superior on paper completely flopped in practice, while the one that seemed worse actually knocked it out of the park. What were they missing?
Well, the answer, it turns out, was that they were measuring the wrong thing entirely. The traditional ways of judging AI confidence were looking at the problem from completely the wrong angle. So the researchers had to invent a whole new yardstick. So, to solve this paradox, they came up with this new metric, within question discrimination, or WQD. And this is the absolute key. WQD doesn't care if an AI knows a question is hard in general. It measures only one thing. For this single question I just asked, can the AI tell the difference between a good answer it came up with and a bad answer it came up with?
And here's why those old metrics were so misleading. They were focused on comparing one question to another. So they were good at telling you if the AI thought a complex physics question was harder than a simple math problem. An AI could get a perfect calibration score just by saying, I'm 5% confident for all its physics answers and 95% confident for all its math answers.
But WQAD asks the question that actually matters for CNESSC. It asks, look, for that Apple question, you gave me 2 different answers. Can you tell me which one is better? That's a fundamentally different and way more useful skill for this task. It's not about comparing questions, it's about comparing the answers to a single question.
And this quote from the paper's thought experiment just nails it. A confidence signal that only says, this question is hard, is totally useless for picking the best answer from a group of attempts. You need a signal that can actually tell the good attempts from the bad ones. That well-calibrated verbal confidence was just saying the question was hard. The P-True method, on the other hand, was actually judging the answers.
Okay, so now that we've cracked the code on this whole confidence paradox, what's the actual payoff? What does this all mean in practice? Well, it's huge, both for efficiency and for what it tells us about what AI can do. Here it is, the headline number, a 46% reduction. Using the right confidence metric, CISC gets the same or even better accuracy as the old way, while cutting the computational cost, the number of answers it needs to generate, by almost half. That is a massive, massive efficiency gain. And this chart from the research just shows it even more clearly. Look at this. To get 70% accuracy, the old self-consistency method needed 30 different samples. But with CISC, you can get higher accuracy, 72%, with just 8 samples. That's better performance for less than a third of the work. It's just wildly more efficient.
So let's just wrap up what this all means. First off, CSC is a simple drop-in replacement for the old method, so it's super easy to adopt. It gives you better accuracy at a much, much lower cost. And what I think is fascinating is that when they had human experts look at the AI's reasoning, the answers the AI rated as low confidence were the exact same ones that humans flagged for having bad logic. And maybe most important of all, this whole thing suggests that these models have a real, genuine ability to judge the quality of their own work.
So let's end with this final thought from the researchers themselves. This isn't just some clever engineering trick to save money on server bills. This research provides some really compelling evidence that these large language models are starting to develop a form of self-assessment, which is a critical step towards AI that we can actually trust. The question we're left with isn't really, can an AI know when it's wrong anymore? The real question, the one we have to answer now, is how can we best harness that knowledge?